coordinate bond. It is also called as a semi-polar bond or dative bond or co-ionic bond. So what is this? It is a special type of covalent bond in which a shared bond pair of electrons. So here shared bond pair of electrons, this is the important point, is donated by one atom. So one atom is donating shared bond pair of electron. This is called, that atom is called as donor and other atom is called as acceptor. So this bond is represented by an arrow. This arrow, this is your tail. This is a donor atom. Donor atom is giving to acceptor atoms. So let us see through one example. So this is a one atoms A, which have full electrons in their valence shell. So here you can see 1 to 8 electrons are there. So but in another atoms B, which have 6 electrons there. So to complete the octet, it requires 2 more electrons. So what happens? These 8 electrons, they will donate 2 electrons to B. So here it is donating. So this is a combination of A and B. This electron is donating to B atom. So this is donated by A to B. So and donating means it is sharing. Pair of electrons donated by one is sharing. So by donating means sharing. It is not a transfer, it is sharing. So in this way, this shared electrons are represented by this arrow. Means since these 2 electrons belong to A, so it is donated to B. So B also a part of electron is shared by the B also by the A. Okay, but actually these 2 electrons belong to A only. So full right is A. This electron, full right of electron is belong to it, but less right is B. But this is just sharing. Anytime A can take it, again B become B will having a previous positions. So here we can say an atom with complete octet or lone pair of electron may act as donor. So this is it can be a complete octet, or if it has a lone pair, then it may act as donor. Say you can see ammonia. Ammonia, this is a lone pair. So this become a donor atom. In water, so oxygen central atom, it has 2 lone pairs. So these 2 lone pairs act as a donor atoms. Again, atoms whose octet is incomplete and have vacant orbitals. So they have vacant orbitals, they may act as a acceptor. Like example BF3. So BF3 have vacant orbitals. So you can see one example, ammonia and BF3. So here ammonia have a lone pair of electrons, so they act as a donor, but in so BF3 boron has a deficient of electrons, they are like acceptors. So you can see the lone pair is given to boron like this one. So these 2 molecules will become one complex. It's called as ammonia boron fluoride complex. This is called like this complex. Okay, so we see some more examples like oxygen molecules. In oxygen molecule, this is a complete molecule. This is a one oxygen atom, means you can see one oxygen is there, so it has again one less electron. So this one lone pair can given to this oxygen. So you can see here in this picture, so this is oxygen, so one lone pair is used to give this oxygen. This is a shared, so this bond is called as coordinate bond. So again this oxygen have a their own 6 electrons and 2 electrons given by this oxygen. So this will having a one complete octet, and this is having a one complete octet, and this is having one complete octet, 2 electrons this side. So 4 plus 4, 8 electrons. So again this will be having a 8 electrons, and this having a 8 electrons. So we can see that octet is completed. So this is a coordinate bond, but this is a covalent bond. So here covalency of this oxygen is 3, but here covalency of this oxygen only 1, and here covalency of this oxygen is 2. So mark it here. Next is your carbon and oxygen. In this you can see here carbon has 4 electrons in its valence shell, so this is acceptor, and oxygen 6 electrons, so this is a donor. So in carbon monoxide molecules you can see here there is 2 bonds between these carbons. Okay, here so here oxygens can require only 2 electrons from the carbon, and carbon has previously 2 electrons. So 2 electrons from the oxygen will be given to this carbon. So carbon will have how many electrons? 2 plus 2, 4 plus 6, and plus 2 given by this oxygen. So it have again how many? 8 electrons. So again this oxygen is having also 8 electrons, 6 and 2 lone pair is remaining behind. So 8 electron here, 8 electron here. So here this is a coordinate bond and 2 covalent bond. Similarly, you can see here ammonia and this one proton H plus, means they have no electron valences, only proton is there. Here lone pair, so lone pair is given to this hydrogen H plus. So here we can see there are 4 bond pair, no lone pair is there. Ammonia is 1 lone pair, but here it says 4 lone pairs. So 3 covalent, 1 coordinate bond, 3 covalent bond, 1 coordinate bond, and it becomes a ammonium ion. Now after this we can see next is characteristics of the coordinate compound. So in physical states, this may be solid, liquid or gas. melting and boiling point intermediate between covalent and ionic compounds, it is intermediate. Solubility, generally they are less soluble in water but more soluble in organic solvents, and they have high dielectric constant. So already we explained dielectric constant is a property in which the type of solutions can make weakens the electrostatic bond of attractions, force of attractions, and they can separate this molecule. So they can do it. They have high dielectric constant. They are the bad conductor of electricity because they do not ionize the matter. So their bonds are covalent bonds are so strong, so they cannot be ionized it. So they have bad conductor of electricity. Stability, it depends upon the nature of donor and acceptor of the acceptors. If these donors and acceptors will separate easily, so they are less stable. But if their donor and acceptance are more strongly bonded, then they are more stable. Again, they are rigid and directional since they are covalent bond compounds, so they able to exist as a stereoisomers. So we will discuss more about this stereoisomers in organic compounds, carbon organic compounds. So we will see later on. So they one more property is they undergo slow molecular reaction. So these type of compounds, when they make complex, the reaction is very slow. So our next topic is polar and non-polar covalent bonds. Polar and non-polar. So let's see one example. So there is a two atoms A and A, and this is bonded by a one bond. So this bond is actually it is two electrons. So here shared pair of electrons is situated at center, and two atoms remain electrically neutral. So this is center. These two electron centers, and this is electrically neutral. But in this case, you can see this shared pair of electron. Shared pair of electron is again it is shifted to this side towards the B, more towards 3. So this B get more negative charge and this A get more positive charge. So this is shifted here. Why it is shifted? Because B is more electronegative, A is more less electronegative, means more electropositive. More electropositive. You can say this is more electropositive. So here bond pair is shifted towards the B due to its high electronegative character. So it results in the formation of a dipole. So when two charges they are negative and positive, so this is called as a dipole. So this is a polar molecule. So which are the examples? Generally this is found in heteroatomic molecules, and these are non-polar, and this is found in a homoatomic molecule. So they are non-polar. Homoatomic means Cl2, O2, N2. These are homoatomic molecules, so these are non-polar. But in HCl, you can see here Cl is more electronegative, so this will be a polar molecule. H2S, H2O. So they are the polar molecules. Okay, they are polar molecules, but you see here CO2, this is a heteroatomic molecules, but this is their symmetrical structure. CCl4 symmetrical structure. Similarly, we have example of CH4, they have symmetrical structure. So again, these are also called as a non-polar molecules. We will study more in higher class. H2H, H2O, this polar, oxygen more electronegative. Why they are more polar? Because they have lone pairs, so they do not form symmetrical structures. Okay, so due to symmetric structures, molecules can be non-polar, but if the structure will be not symmetrical, the molecules cannot be non-polar. It will be polar molecule. So next our bond is a metallic bond. So in metallic bond, it is actually force of attraction which holds the metal atoms together in a metallic solid. So it is different from ionic and covalent bonds. How it is different? So let us see this one. Electron C theory. So this is one theory given by Drude in some 1900 years. So what he proposed, electron is a gas or electron C. Here we have to understand what the two terms. One is called as kernel and other is called mobile electron. What is the meaning of kernel? Kernel means nuclei with co-electrons. So I have given one example here. So this is the example of sodium atoms. So here you can see it. This is the nucleus. Electronic configuration is 281. So for nearest orbit is 2 electron. Then L cell is 8 electron. And last is 1 electron. So this nucleus plus this whole is called as K, and this K cell, L cell plus nucleus is called as kernel, and this electron is called mobile electron. So two term mobile electron which is free in motion, and kernel is nuclei with co-electrons. So this you have to keep in mind. So a metal comes to here. A metal consists of so many atoms. So these are the nucleus and these are the valence electrons which can be freely delocalized. It can come this side, it can come this side, it can come this side, which can be freely delocalized. Due to it has so many properties. So here so take this one case. So there are two nucleus, so they can repel each other, but electron is present in them, so they can attract each other. So due to this net attractive forces, so these bonds become more and more strong. Here, net attractive forces. So here concept is that mobile electrons behave as a ideal gas. So these small electrons behave as a ideal gas and regularly move at random. It can move any direction. I said just now, this side, this side. If it is moving this side, so another electron will automatically will be occupied. It is never even vacant. Second thing, direction of motion is not a definite. It can go any side, up, down, this side, anywhere it can go it. These mobile electrons are responsible for attraction and between these ions, and they are called as metallic bonds. So due to this, the bond is metallic bonds. Now second, strength of metallic bonds increases with number of mobile electrons between two cations. So when the number of electrons increases, then metallic bonds will be more stronger. Second point, increase in effective nuclear charge. So here, due to if you take the more large nucleus, so effective nuclear charge will also increase, and that's why alkali metals are soft metals. So when you go down in alkali metals, like group 1 metals, they are normally soft metals. And low melting boiling point, no melting point than the transition elements. So their size is very big because of more effective nuclear charge, and they are more and more soft metals. Now, due to metallic properties, some of the properties defined. So what are those properties? The properties are they are having a electrical and thermal conductance. These mobile electrons can take heat, and they can conduct electricity. So these mobile electrons also help in malleability and ductility. So due to non-directional nature of metallic bond, metallic had non-directional, it can move in any directions, like ionic. So it has non-directional nature. So due to non-directional, it can form ductility and malleability. And this metallic cluster, they have metal clusters, we know that. So electrons on metal surface, they absorb photons. When any light falls on the metallic surface, they get excited, and immediately energy is emitted, due to which we can see the shining of the metal surface. But it has some limitation, that it cannot explain why sodium is soft and osmium is very hard. So there are some problem that is we can define as sodium is soft, but in the same way osmium is a metal, but it is very hard. There is another limitation, that copper is very good conductor of electricity. It is 50 times more good conductor than bismuth. So these are some problems which cannot be defined by the metallic bond.